Well, we've just had a look at Dr. Mike explaining why there are only 5 platonic solids. And I thought we'd just take a couple minutes to review how he came up with this decision. And to begin this review, I'm going to take a look at these 3 platonic solids here, the tetrahedron, the octahedron, and the icosahedron. Notice the tetrahedron has emitting from each vertex 3 triangular faces. There's 1 here, 2 there, and 1 on the bottom we can't see. The octahedron, as you can see from this vertex, has 4 triangular faces that emit from it. And you can see on the icosahedron down here, there are 5. 1, 2, 3, 4, 5 of them emitting from each vertex. Well, is it possible to have a platonic solid with 6 triangles emitting from a single vertex? Well, to take a look at this, we're going to construct very quickly an equilateral triangle here on the smartboard. So I'm going to go up here and draw a nice, fairly large equilateral triangle. All right. Now, to show what the situation is with 6 equilateral triangles going out from one vertex, I'm going to clone this thing 5 times. All right, so I'm going to take this and I'm going to clone it. Here's my first cloning of it. And when I've done this, I'm going to take it and totally rotate it around like so. Okay, so there's 1 triangle that I've cloned, but I just rotated it. I'm going to stick it over here. Actually, I'm going to stick it right up here. Now you'll notice if I get that right in position perfectly, okay, I now have 2 triangles emitting from a vertex, but we need more. We want to see if we can fit 6, okay? Well, I'm going to clone another triangle now. I'm going to take this one down here again and clone it. When I clone it, I'm going to slide it up here, right there. Let me get that in position a little bit better. Pretty close right there. Okay. I'm going to clone this triangle down here again. Of course, when you clone an object, it's exactly identical to the one you had previously shown to it. So, all right, that's pretty good positioning there. Okay, so far I have 4 triangles coming out from a single vertex. And now, of course, I want to get 2 more. So I'm going to clone this one here. All right, so I'm going to clone it. Okay, and bring it down here. Put it in position there. And I'm going to clone that one also and bring it over here. Now you can see I have 6 triangles. You take a look, okay, we have a situation now where we have 6 triangles emitting from the vertex. Notice I've done this on a flat surface. Each of those 6 angles would be 60 degrees. If I multiply 6 times 60, I get 360 degrees. So you can see the figure would be flat. Okay, and that's a key phrase you're going to want to remember when I ask you to look at these situations, is that you get a figure that is flat in a lot of these configurations. That's why it can't be a platonic solid. Okay, let's go to our next screen. Okay, here is a hexagon. Why can't we have figures that are platonic solids which have hexagons on their faces? Well, it's fairly easy to show here. I can simply take this hexagon, clone it, place it down here. Okay, I can clone this hexagon and place it up here. Okay, let me redo this again. Get this turned on, and you can see I can put it up there. And you can see now also, once again, I have a single vertex right in the middle, but only 3 hexagons coming out from it. I've used up everything I can use at that particular vertex. By the way, the hexagon, regular hexagons have 120-degree angles at their, each of their angles have 120 degrees in them, sorry. So if you put three 120s together around that one vertex, you can see it adds up to 360, which makes it perfectly flat. Okay, so with that in mind, let's review some of this material for the big quiz 20 that I'm about to give you. Now, quiz 20 has on it 10 questions, all right, and 4 extra credit questions. I've given you an answer sheet that you can place your answers on. You can either print it or you can type them in there, or whatever works for you. And you can take a picture of that answer sheet and send it to me, and it'll make it easier for me to be able to grade the material if you put them all on the answer sheet. You can take a picture of the answer sheet with your phone if you'd like, okay? Whichever works for you. At any rate, let's review all the material that you might see on Video Quiz 20. So here we go. Okay, it's nice to be regular. Remember this problem I showed you before. You recall that the figures that are on top here are all regular polygons. Remember, regular polygons, all the sides of them are exactly the same length or congruent in length. The sides are made of line segments. Notice the figures toward the bottom are all non-regular polygons, okay? The sides are still line segments, but they are not equal in length, and the interior angles on the insides of the figures are not all identical. Okay, state why each of these plane figures are not polygons. If you look at the first one, it's crossing itself. It's being religious. You cannot have a religious polygon. The line segment sides may not cross over the other sides of the figure. So that's why that figure is no good. If you look down here, this particular figure on your left, it's not closed up, is it? And because it is not closed up, it cannot be a polygon. Or couldn't be a regular polygon either, but certainly can't be a polygon because it has to be closed up. All right, and what's wrong with the figure to the right? Well, one of the sides isn't a line segment, therefore that figure also cannot be a polygon. Let's review some more. So there are only 5 platonic solids, and you see what those are right here, okay? And you know that the definition of a platonic solid is very simply this. In each platonic solid, okay, each face is the same, exactly identical to all the other faces that are in the polygon, okay? Another way of saying that a little more professionally would be to say that all of the faces of a platonic solid are congruent, regular polygons, all the same type. And the other thing that has to be true to be a platonic solid is that each vertex from it emits the same exact number of faces and the same number of edges. All right, so that is the important things that you have to know about the properties of a platonic solid. Down here, we have all this information. You don't really need to know all this information in most cases. However, you have these tables on your platonic solids fact sheet, which you can refer to help you do the quiz. And those tables, of course, are all on there. Let's go on. Let's review dual platonic solids. Now, the platonic solid shown up here is a what? It is a tetrahedron. It has 4 faces, okay? Its dual happens to be another tetrahedron. If you put a dot in the center of each face of this figure, you will get a triangle, a triangle-shaped object, such as what you see here, triangular faces that is, and it'll be another tetrahedron. So a tetrahedron is self-dual. It is its own dual. You will get a tetrahedron that'll be similar to it, but It'll be upside down, and it'll be inside the figure, hooking together all the center points of all the faces. 4, the cube. If you hook together all the center points of the faces on a cube, you obtain its dual. Its dual, as you are going to see here, is an octahedron. Notice the dots are in the center of all the faces. They are hooked together with the white line segments, and they have formed an octahedron. By the way, we should say this, an octahedron's dual is a cube. If you take all the faces of an octahedron and you put a dot in the middle of each of those faces, a cube would be formed inside the figure, okay? They're opposites of each other. What I mean is they are duals of each other, okay? All right, and finally, the most complicated looking figure, the dodecahedron, has as its dual an icosahedron, which has all the triangles in it, as you can see there. So remember what the duals are. They are located on the Platonic solid fact sheet at the bottom so that you know which figures are duals of each other. Here are some more important things that we need to go over in relation to the Platonic solids. Why aren't these figures Platonic solids? Well, first of all, the figure you see on the left, I've shown you this one before, the green top pyramid up there, okay, cannot be two pyramids exactly like that put together, cannot form a Platonic solid, because if you notice from this vertex right here, that I'm putting this little box around here, okay, let me show that more carefully in red. Around this vertex right here, if you count the number of edges that go out from it, there are 4, okay? However, if you look at this vertex back here, there are only how many edges going out from it? Well, I lied to you. There are 4 going out from it also, all right? However, look at this one. There are only how many going out from it? Only 3. Every vertex has to have the exact same number of edges emitting from it, and also the same number of faces emitting from it. All right, look at this figure over here I've drawn the arrow toward, okay? That is a prism. It is not a Platonic solid. Notice all the faces are not identical, okay? So that does not satisfy the properties of a Platonic solid. And remember, of course, the soccer ball. The soccer ball has 2 types of faces in it. One is a hexagon, a regular hexagon, and the other is a regular pentagon. And that can't be in a Platonic solid. They all have to be exactly the same faces. Further reviewing, remember, these are golden sections. In a golden sections, if 3 segments are golden sections, the following 3 properties have to be satisfied. The shortest one, CD, added to the middle length one, EF. Those 2 lengths have to add up to the length of AB. Secondly, if you divide the longest segment, in this case AB, by the middle length segment, EF, you will get phi for your answer. And the same is true about the middle length segment divided by the shortest segment. It will also give you phi. So don't forget that. Those 3 properties have to be satisfied for those segments to be called or be known as golden sections. Remember, in the drawing of a figure like this, okay, which is obviously a what? It is obviously a rectangle, which is golden, all right? In this golden rectangle, there is a square, which is 2 by 2 here. If I take this square, okay, and I look at the triangle that is drawn inside of it, it has a special name. that triangle is referred to as a golden triangle, because remember, this golden triangle has the properties that its legs are related, that one is twice the length of the other. Not the hypotenuse now, but one of the legs is twice as long as the other. Any right triangle that has that property, where one leg is twice the length of the other, is known as a golden triangle. So keep that in mind. So this completes our review to get you ready for Video Quiz 20. Video Quiz 20 is a 10-question quiz with 4 extra credit questions on it. And I'm hoping that you will be able to do very well on this quiz. So your assignment for the weekend is to complete this quiz. I would like you please to use the answer sheet that I've supplied with the quiz at the very end of it, to use it to record your answers, all right? And you can just take a picture of that answer sheet and text it to me with your answers upon it, okay? That would be extremely helpful. In addition to getting that quiz to me, if you have not sent 17, quiz 18, or quiz 19 to me, I would like you please to get those sent to me as soon as possible as well. Also, I would like you to be very sure to make certain, that is, that you have sent me your quiz number 2, which was called Virus Quiz number 2, so that I will be able to grade that for you as well. In addition to this quiz that I've assigned, number 20, I would like you please to, over the weekend, take the time to watch 2 more videos, presentations, which are indicated in the email to you. Their URLs are there. One is called Platonic Solids Part 1, and one is called Platonic Solids Part 2. And those 2 videos were made professionally by someone else, and I think they are excellent. So watch those as a good review of the Platonic solid material that you have seen. I hope you have a very pleasant weekend, and I will talk to you next week. Take care.